Thank you very much. Welcome to the second part of this lesson. And I want us to look at the race condition. You've already seen an introduction to the concurrency process, whereby you said that these are processes that are executing the same piece of data, and it is shared in a way. And we have seen some of the issues that are involved, whether you are executing the process in a single processor or we are doing it in a multiple processor. There's that issue that several issues that you have said, 3 of them that you have said that will arise. And one of those problems, you can simply define it as the race condition. And I believe the first problem there, we saw it that when two processes that are working together share some common storage, e.g. memory or file, that each process can read and write. When two processes are reading the same shared data, then the final result will depend on who runs precisely when. And we say that these processes are in a process that are in a race condition. In other words, they are competing. Meaning, if they are able to, or the other is the final result will be dependent on the order in which these two processes will be executed. So if they are sharing a piece of data, it's modifiable, or both of them are able to make some changes on it, be it a file or be it a memory, then the final result will depend in which process runs when. Concurrently executing threads may also share some data, a need to synchronize the operations and processing in order to avoid race condition on shared data. So sometimes also the threads also have the race condition if they are sharing some piece of data, and they need to synchronize their activities so that they can have they can have that uninterrupted operation. The race conditions are also possible in operating system, especially in when it comes to managing the queues. So if the ready queue is implemented as a linked list, and if the ready queue is being manipulated during the handling of interrupts, then the interrupts may be disabled to prevent other interrupts before one completes. And if the interrupts are not disabled, then they could become corrupt. But simply the race condition simply talks about these processes that are executing simultaneously, and they are sharing some resource, and this resource or the final result is dependent on the final, or that is dependent on the process that executes first. Before we get to the what we call mutual exclusion, allow me to look at what we call a critical section. And a critical section is one of the ways of avoiding race condition. And the critical section is a section or in a program execution, or on that part of the program that we are referring to as critical, that is that is sharing data with another, then that part, because if you look at the programs, now the whole part of the program is sharing those resources that requires, or that requires the whole of those resources, or not the whole process that will require the resources. There is a specific part of that of those two processes that may require those resources, that shared resource, and that particular part of the process is what we are referring to as the critical section. So the key preventing trouble involving shared storage is to find some way of prohibit more than one process from reading and and writing shared data simultaneously. So, and how to do it to prevent this process from reading and writing the shared data simultaneously, even if they're executing at the same time, we just need to know which exact is this part that wants to do or to access this data of the program for both programs. If there are two of them, you check the two, and that part we refer to it as the critical section of that particular program. Meaning, when it starts executing, or that part of the program start executing, you stop. You don't allow the other program to be executing the other part or its critical section, or that section of the program that requires to access that data. So that part of the program that part of the program where the shared memory is accessed is called the critical section. And each of the two programs has its own critical section. Remember, they want to access the same data. And to avoid race condition, you just need to identify those sections, the two sections for each program, and ensure that the operating system will ensure that the two of them do not execute at the same time, or you shall be saying that this process or these sections do not execute, or the two sections do not execute at the same time. And to avoid race condition and for results, one must identify the codes in the critical section. So, or in the critical sections, these are now two, there are many critical sections, and meaning that you must identify those codes in the critical section, that is in the critical section for program one or process one, and for process two, those processes that want to read that particular shared piece of data. And there are 4 ways in which you can identify those codes, or those part of the programs that can form a critical section. And you must identify them with in reference to either the shared piece of data or the shared memory where they want to that they want to access. And we have said that these critical sections, they are sections or they are parts of the program that want to access this shared data or shared variable. So the first way that you can identify them, or these parts or these codes, is that it is a code that references one or more variable in read, update, and write fashion, while those variables are being altered by another process or by another thread. It can be a thread, it can be a process. So it is referring to them, or that code is referring to them, but those variables, they are being changed, or they are being altered by another process or by another thread. And also the opposite is true, that this process that is also altering, these codes that are also altering this data that is being referenced, then they should also be taken to they should be part of the critical section. That there are codes that alters one or more variables that is possibly being referenced in a read, update, write manner by another process or by another thread. So the first two are just opposite of each other. That code that is referencing and that code that is altering, then those two processes must be, or those two sections must be identified and be made to be part of the critical section. Then the codes that use data structures, while any part of it is possibly being altered by another process. So in this case, we are comparing those that are using the data and it is being changed. So the two of them must be the one that is using and the one that is altering. Both of them must be done. What must be made to be part of the critical section, or must be identified as critical section. Then fourth, finally, it's a code that alters any part of the data structure, where it is possibly being in use by another thread or by another process. So those codes that are using when it is being altered, or that are referencing when it is being altered, then those codes must be made to be part of or that it must be identified as part of the critical section. And those codes, if they identified, they'll assist us not to have to create an order and not have two processes accessing the same piece of the data simultaneously. And they'll also assist us in achieving what we call mutual exclusion. And I think that one has been defined here, but we're going to define it down here again, mutual exclusion. Yeah, if those codes that are in critical section are not being executed at the same time, then we say that those two processes are have been mutually excluded. And this leads us to another subtopic that we refer to as mutual exclusion. And I want to be a bit fast. Mutual exclusion is a way of ensuring that if one process is using a shared modifiable data, the other process will be excluded from doing the same thing. So this is just ensuring that this process, though they are sharing this data, they are not allowed to use that data or to execute the data or this shared modifiable data on the same, that is at the same time. And this is done through mutual exclusion. So while one process executes the shared variable, all other processes that desiring to do so at the same time, at the same moment, should be kept waiting. And when the process has finished executing the shared variable, one of the process waiting, while other process finish executing, they should also be given a chance to come to get to that hot, but they should not be allowed to access the data simultaneously, that shared modifiable data simultaneously. And this is what we are calling mutual exclusion, that these processes are mutually excluded from accessing the same piece of data simultaneously. There are some requirements for mutual exclusion to be a success, or for process to be mutually exclusive. There are 6 requirements that must be held in place. Number 1, the first requirement for mutual exclusion to exist is that mutual exclusion must be enforced. Mutual exclusion must be enforced. In other words, only one process at a time should be allowed to get into the critical section. Remember, I said that is only one process at a time is allowed into critical section, and the other process that wants to execute the critical section should not do the same, or should not be allowed to do the same. They should be made to wait. So critical section, you have said, remember I said this is a process that is trying to, that is the section of a process that is trying to access this shared modifiable data. So when one process starts executing that section, its own section, then the other processes, all the other processes that want to execute their critical section, trying to access the same data, they should not be allowed to do it. That's what we call enforcing. The other requirement is that a process that halts in its non-critical section must do so without interfering with other processes. So if one process stops abruptly in a non-critical section, then it should do so without interfering with other process. If it is in a non-critical section, it should all the other process should be allowed to get into the critical section, and the processes must continue. Then the other requirement is that it must not be possible for a process requiring to access to critical section to be delayed indefinitely. So these processes that are halted and they want to access their critical section, if they have been halted, then there should be a mechanism not to avoid starvation, that this process have been starved simultaneously, or that is a halt indefinitely. Then number 4, for no process in the critical section, any process that requires entry into its critical section must be permitted without any delay. So if there is no any process that is executing its critical section, any other process that wants to do so should be allowed without being delayed at all. Then there should be no assumption that are made about relative process speeds and number of processors. So you should not make an assumption that after 10 seconds, this process should be out of the critical section. You have 3 processors, meaning that this process should be out of the critical section after 10 seconds and so on. Then you should not make those assumptions, because you may end up putting one or two process into the critical section, which is not advisable. Then a process that remains, finally, the final condition is that a process remains in its critical section for a finite time only. No process should be allowed to stay indefinitely into its critical section. It should be within a defined amount of time that this process is allowed to stay into its critical section. How do you achieve mutual exclusion? There are 3 ways of achieving mutual exclusion. One is disabling interrupts. Disabling interrupts, or what we call hardware solution. And this is how it happens. Each process disables all interrupts just after entering its critical section, and re-enable all interrupts just before leaving the critical section. And this will enable no other process. So we can achieve mutual exclusion by disabling interrupts. So when a process gets into the critical section, it will enable all the interrupts, meaning it cannot be interrupted until it finishes the critical section. And it will do what? We shall not be having any CPU or CPU trying to switch off to another process happening. So this process will be allowed to execute in and finish through its own, or that is through its own critical section. The other way of achieving mutual exclusion is through what we call lock variable, and this one we refer to it as the software solution. Software solution, this whereby you have a variable that you call lock, and it is shared amongst the various processes, or it is connected to the resource that this process or the process are sharing. And this single process, it's binary in nature, meaning it can have either a 0 or 1, and it is initially at 0, meaning when there is no process that is in the critical section, this variable is 0. And when a process wants to get into its critical section, it will first of all check this variable. If the variable is 0, then the process will do what? Will get into the critical section and reset that variable to 1, and then the process will get into its critical section. And when it is already it is 1, any other process that tries to get into the critical section will not be allowed to do it, because it's only the process that can change it, or this process that changed it from 0 to 1, it's the only one that can change it. And by so doing, any other process, we shall be having mutual exclusion because no other process will be allowed to start executing its own critical section. And when this process that is in critical section finishes executing its critical section, it will reset the variable back to 0. And this means that when it is at 0, there is no process that is in the critical section, and any other process that that was stopped from doing what? From accessing this, or that is executing its own critical section, will be done what? Will be allowed to move on and continue executing. And with a lock variable, we should not be able to allow more than one process to execute or to execute its own critical section. The other method of achieving mutual exclusion is what we call strict alteration. Strict alteration. In this case, we have an integer, and this integer we refer to it as tan, and this is tan in quotes, meaning it will do what? This integer will keep track of whose process, whose turn it is to get into the critical section. So if it's meaning each process will be having this variable or integer variable, and this integer variable can take two forms, either a 0 or 1. When it is a turn of a particular process, then it's what? Its turn variable will be a 0. And if it's not its turn, then the turn variable, its turn variable will be 1. And this process, or that is if a process would inspect the turn variable, find it's at to be 0, then it would enter its critical section, and it gets into the critical section. The next process that comes in will do what? Will wait for it to change. So the turn variable changes between 0 and 1, depending on whether or on what the process comes in. So it will keep on changing. You must wait for it to change, or the turn variable or process must wait for it to change, and it will be changing from 0 to 1. So when the first process finds it at 0, it will get into the critical section. But when the second process comes and finds it at 0, it will do what? It will wait for it to change, maybe to change back to 1. When it changes back to 1, this process will continue executing. When the third process comes in, find it at 1, it will continue waiting to check whether this process have changed, or this variable have changed, meaning it will change between 0 and 1, depending on what on the process number. All the even number processes will find it at 0, or will execute when it is 0. And all odd numbers processes will execute when it is 1. So the first process will execute when it is 0, that is 1. No, all the odd numbers will execute when it is 0, and all the even numbers will execute when it is 1. And they must continually check. And if the number is odd, it will continue a check until it changes back to 0. And sometimes we say that this continuous checking, we say that the process is busy waiting, and it is busy waiting for the process to change back to what? To either a 0 or 1. There's also another way of achieving mutual exclusion, and this is through use of what we call sleep and wake up system calls. sleep and wake up system calls. They are ways of also achieving multi-exclusion. When a process wants to enter into the critical, that is, wants to get into the critical section, it checks if the entry is allowed. And if the process is not allowed, the process goes into a tight loop and waits. In other words, it starts to be busy waiting until it is allowed to enter. This approach of busy waiting, that is a sleep and wait, will do what? Will waste a lot of CPU time. And we have two ways of communicating. One is through sleep and or through that is through sleep call and through wake up call. When a process is not allowed to get into the critical section, or it's not allowed to get into the critical section, it is given a block through what we call a system call known as sleep. So the sleep will make is a system call that will make that will cause the caller to be blocked and suspended until some other process wakes it up. So in this process, then there's a wake up call that will be made by the process that was already in the critical section. So as it leaves the critical section, it will do what? It will make a wake up call and wake any process that is a hot, that wake up any process that was made to sleep and wait for its turn to get into the critical section. So this is also another method of achieving or mutual exclusion. So in a nutshell, we have three ways of achieving mutual exclusion: through the sleep and wake up call, through the strict alteration, through the lock variable, and through the hardware support, or what we refer to as disassembling of interrupts. With that, I beg to stop at that for today. In our next lesson, we shall be looking at the other methods of inter-process communication, and we shall be delivering it next week online. So you may have a nice time.